All right. So my company started from the foundations of biopharma industry, and we developed our products called BioSettlers or inclined settlers for mainly the biopharma industry, exactly as the previous speaker mentioned, for perfusion applications. Gradually, we found some of our customers were from the cell therapy industry and even more recently from cultured meat industry. So I am expanding my horizons and thinking about how I can make it more useful for not only cell therapy, but also for cultured meat industry. So that is the background on where we're starting. You will see mostly all the proven examples data from the biopharma and maybe cell therapy a little bit. But for cultured meat, I'm definitely looking for collaborators who would want to test it in collaboration with me. I know that whatever we have done with Chinese stem cell cells or human embryonic kidney cells, other people have done for iPSC cells, etc., would be readily transportable. So to give a quick background, when I was a professor at University of Colorado a while ago, I was introduced to the concept of inclined settlers by people in fluid mechanics areas of my department. And I wondered if I can use it as a size-selective cell separation device. And the very first time we tried with my second graduate student, Brian Batt, and a fluid mechanics colleague, Robert Davis, we proved that this device works very nicely to remove dead cells and smaller cells or cell debris from the top of the inclined settler, and the heavier or rather faster settling larger cells, typically live cells, are returned back to the bioreactor. Can you all see my cursor? I presume?
Yes.
Great.
Yes.
So this inclined settler is an alternative, my preferred alternative, to a typical microfiltration membrane for a couple of reasons. One, it has no barriers and cells will not clog anything here. There's no membrane here. And second, it is selective, meaning I can take away the dead cells or secreted proteins along with the harvest and send the live cells back into the bioreactor, which will cause the cell density to be high. And one can run this for literally forever. I did not start a company at that time, and so ATF became very popular. But some people who scaled up inclined settlers on their own have run this bioreactor, so-called perfusion bioreactor, for 3 months or 6 months, as I have been told, in public disclosures. So this actually is I'm going to go to my next screen. There we are. This is actually a easily scalable system. In figure 1 on the top left is one of the ways that my little glass device in 1990 has been scaled up by others. Dr. Peter Brown was at Chiron, and then he started his own consulting company after taking retirement from some other companies. And several different sizes of this are available and are in different countries even. On the top right is a much larger version of it I saw published in 2013, and they were actually very happy with this as a seed train replacement for a 3,000-liter perfusion bioreactor. This is from Roche in Germany. But when I saw it, I saw a problem. They were happy with it, but I saw a problem. There's a huge footprint that is really not used at all just to hold this up. And I realized that it is much easier, much more compact to scale it up if I put my inclined settlers inside in conical form, and have shown my first version of what we call compact cell settlers. It works exactly by the same principle as the inclined settlers. All the inclined surfaces are in the form of cones inside this 4-inch diameter, 6-inch diameter, or 12-inch diameter volumes are 2 liters here, and this is about 15 liters in the internal volumes. And it's all stainless steel, and we can sterilize it with steam, autoclave it for small sizes, etc. So this works. The capacity of this more efficient, compact scale-up design is for the same footprint. This has about 6 to 10 times higher settling velocity. So you can actually use it for any larger, instead of saying 3,000 liter perfusion bioreactor, you can even use it for 30,000 liter perfusion bioreactor if there is a need. Along the way, the industry said, can we make it in single-use disposable plastic? And this is our first version of it. What you can see here is, I have another slide going into a little bit more detail on this, but there are no moving parts in this device other than the liquid that is being pumped in and out. By doing some clever process chemistry, like adding acetic acid or citric acid, we clump the CHO cells into aggregates, and they settle down. As soon as you stop flow, as in comparison to a future diagram, the cells settle down as if they were pelleted in a centrifuge. But remember that there are no centrifuges here at all. It is a very simple device. And in fact, I think this is a great way to concentrate cells gently for bioprinting applications in cultured meat. I haven't done it, but these are some of the things that we can explore in collaborations. So these are the original applications using the settler single cells as a perfusion device, cell retention device, selective. Dead cells are taken out along with the harvest media containing secreted proteins. The live cells are more in number, and they're all actually 100% returned back to the bioreactor here. And we know that by measuring the size of the particles or cells in our liquids, if you just take from the top effluent, in one of what I call a failed experiment where the viability in the bioreactor was about 50%, and you can see in the blue line, there's a small peak for dead cells, a lot of cell debris. Our settler is able to remove selectively the dead cells, and the question at that time was, what's happening to the live cells? In the next time we did it, previously it was in April of 2017, now it is in June of 2017, we actually took a sample from the bottom return before it gets to the bioreactor, and we can show that the larger live cells are actually going back into the bioreactor, and cell debris is being selectively returned back into the, being returned. Cell debris is being removed from the bioreactor along with the secreted products in the media. So that was the original application. Some people who make their own settlers do benefit from these things, but we now have a new company and we can sell these devices for anybody, so you can use it off the shelf. Here's a different application. In fact, the title of this slide was different, but I flipped it around and said, it is also useful for concentrating CHO cell aggregates very gently, because there is no centrifuge here, no membrane filtration, nothing getting clogged. And you can, if you want, continuously take the concentrated cells from here and send it through a bioprinter, and the spent media can be removed like this. So the other application we had was to collect antibodies through here. But if you're more interested in the cells, we have a very concentrated cell pellet when you stop the flow. If you don't stop the flow, it will continuously flow into potentially a bioprinter. So as I was talking about these things, other people started buying our settlers, particularly Sema Therapeutics, before it got acquired by Vertex Cell Therapies. We're interested in harvesting beta cell islets from iPSC cultures. And so that is when I thought, this could be useful for cell therapy applications. And at a conference from, let's say, Advanced Regenerative Manufacturing Institute, we found a collaborator who had a pain point, and I'll get to it in the next slide or two. And we think there are many other applications, including, for example, microcarrier beads can be easily removed from any MSC cells that have been grown to confluence on them and then detached from them. And there are many, many applications I can think of. All of these are in cell therapy. So this is a different audience. My hope is to convince you that it is also useful in the cultured meat industry. So along the way, we have changed this design so that it can be made bigger, like longer and even longer. And we have, instead of a 1,500 milliliter, we have a 2,000 milliliter BioSettler instead of 500, which is exploded in view, showing the internal inclined settling surfaces in the form of stacked cones. We also have, and you will see it in the next slide also, 250 milliliter BioSettler. So here is the problem or pain point that Pluristyx company, which specializes in induced pluripotent stem cells, their product is ready to differentiate cell clusters or organoids. When they were growing it in a popular vertical wheel bioreactor, which has a well-defined low shear pattern, and so stem cells are not subjected to high shears of an impeller or an agitator. So it had many advantages. But its problem was when they were taking samples, or the stem cell cultures clearly need frequent media replacements because of growth factors not being very functional for more than a few days. So after day 3 or so, they have to stick in a pipette and take out the liquid. And they found that the media contained all the aggregates as well. And that was their pain point. And they asked me, can my settler do that? And they were dealing with smaller volumes, like 500 milliliter bioreactor. So I gave them a tiniest version of the settler we made, same diameter as before, but this is 250, a little bit shorter. It had about 8 cones or so inside. Instead of a vertical wheel, they had transferred into a spinner flask, and they were taking samples from whatever is coming down here, what I call bottom return, taking samples from whatever is on the top perfusate, or I call it top effluent. So the data provided by Pluristyx is here. This left panel is what is being sent into the BioSettler. It has a mixture of organoids and single cells, cell debris. Single cells, it turns out, is not desirable for them because it might be a hallmark of a differentiated cell population rather than stem cell population. And clearly, nobody wants the cells, debris or dead cells. So the bottom is really enriched with the organoids. And the top effluent contains mostly single cells or maybe very tiny pellets or tiny clusters. But the size bar, this is 500, this is probably less than 50. Their goal was to keep all the aggregates above 100 micron size back into the bioreactor. So this is the first time they used it, and within 2 hours, these are the results. Even after 20 hours, the results are very similar, and they could use it for more if they wanted to. But their pain point was that they were worried about, okay, inside the settler, if we don't control the pH and temperature and dissolved oxygen, then maybe stem cells will differentiate there or something else. So they were worried about it. So with the same funding from ARMI, we inserted what are known as single-use disposable fluorescent dye sensors at the bottom of this tube, and we can insert them at different heights around the periphery. And we can also insert a thermocouple in through one of the other peripheral ports. And with some help from a collaborator by the name Rockwell Automation Company as a cost share partner for this ARMI grant, we were able to, you will see in the next slide how we can control temperature and pH. These are the polycarbonate tubes of different heights at which we can introduce at the bottom of it very different fluorescent dye sensors for pH, DO, or have a thermowell for thermocouples, etc. So this is the expanded view. And what you can see is there's a lot of stacked cones. We can scale it up any way we want. And this becomes relevant when we come back to cultured meat industry. I'll talk about in a few more minutes. This is the proof. You can see a lot of stacked cones with some kind of controllers in here and tubing and a user interface. And this is a few days later. This is at the time of the inoculum. This is a few days later. And we were doing CHO cells, which are in suspension. But now we are growing the HEK cells, which take both suspension or adherent surfaces. And the cones can be made porous if you want, using things like porous 3D printed polylactic acid, or maybe in cultured meat industry, one can use, let's say, molded edible fibrous material left from mushrooms, or the material can be anything you want, and you can have cells growing on top and through the porosity of these inclined surfaces. This slide shows pretty much like what is the pH here, the temperature, the dissolved oxygen, how we are improving the control of it by alternately feeding either air or oxygen as needed. All this is automated by Rockwell Automation. And with this, we really don't need to pay attention to the daily operations. We have run it for 43 days until some vacation came along, or maybe it got contaminated due to media switch. I don't remember the exact details. This was during a vacation. I can see this gap. And this gap, I was lazy to go to the lab on a weekend, I think. So on and so forth. The point is, this can be run for as long as you want, just like other companies who have used settlers have run it for 3 months or 6 months, and depending on the need. The point is, our BioSettler has now become converted into an inclined settling bioreactor. We can continuously remove the medium, we can continuously perfuse the fresh medium, and we can remove any dead cells, cell debris, etc., that are loosely floating around. And if our cells are growing attached onto the top of the cones, then we definitely have a concentrated cell mass growing in here, growing inside the ISB. And this is just showing dissolved oxygen, how it is maintained even beyond 20 days. Temperature, we are improving the temperature control, which is some of the easiest things to do, and we ignored it for a while, but now we are using Rockwell to automate, and it should be maintained very close to 37 or whatever the set point may be. There are, for a variety of scalable cultures, people use tissue culture flasks of various sizes and the surface areas required. We know we can make it in any size we want. As you have seen, 250, a very small version of it. We have made 250 milliliters. We have made 20 liters inclined settling BioSettler. We can easily put probes into this and make it into an inclined settling bioreactor. So this is ready for use in the cultured meat industry. Let us skip the first 3 bullets, which are all saying that we have proven it, we have used, it's very compact, and these are all cell therapy applications. Most of this audience in cultured meat industry, we believe very strongly that the ISB can be used to culture meat in a closed, sterile, scalable, controlled bioreactor, where the inclined surfaces can be porous surfaces made out of either this is something I do routinely, biodegradable polylactic acid, glycolic acid mixture, which will make sure that they don't degrade as the cells are growing, but over time, and these are food grade, one can potentially use this. Or if your company is more interested in putting some other substrate onto which your cells will attach and grow, we can make the cones out of such fibers. And so cells will grow in 3D throughout the cones and also grow out away from the cones. And during the growth process, you have a media that is circulating through the cones, the pH and DO are maintained, temperatures maintained. So this would be a great way to scale up cultured meat. That is the end of my prepared slides, and I would be happy to address any questions and look for collaborations for novel applications in the cultured meat industry.